So now this last week I haven't been doing anything electronics wise, although videos have been going live because I uploaded them a while ago. Pretty much every day they went live. And so I just figured I would do a quick review of these drawings I put together. So it's not a bad idea when you're starting off in electronics. Get familiar with the 1000 ohm resistor. So if you have the blue ones, which are most common now, the blue ones that are rated for a quarter watt, there are larger ones, but quarter watt is the most common size. Then this is the tolerance band right there. You want to put it to the right. For the 1000 ohms, it starts with a brown band, and for 1, and then you got 0, and then we got another 0. So 100 basically, but there's another digit. So this is actually the multiplier. For brown, it means times 10, or you could think of brown as one more 0. So 1, 0, 0, 0 for 1000 right there. So the current that flows through the 1000 ohm resistor right there. So current is the voltage divided by the resistance. Pretty straightforward. You got 1 divided by 1000, you get 0.001 amps, but it's more commonly referred to as 1 milliamp right there. 2 volts divided by 1000 is 0.002 amps, which is 2 milliamps, and so on. Now we have to worry about the resistor heating up. We saw you double the voltage, whatever voltage you're doubling, you'll get twice the current right there. Pretty straightforward. But you happen to get 4 times the wattage. It's going to heat up 4 times as much, and it must dissipate that heat. Most of them are rated for a quarter watt, which is 0.25 watts. So you can see when you got 11 volts across the resistor there for 11 milliamps of current, you got 0.121 watts. So 0.25 is the maximum. You want to stay about halfway below that. So 0.125 watts or less is a goal, and we hit that there. You'll see this resistor in 12 ohm circuits, or 12 volt circuits I mean, quite a bit. I use it to protect LEDs. That's because out of that 12 volts, the LED drops about 2 volts, and so you actually end up with 10 volts across the resistor in most cases, protecting an LED. Some LEDs drop 3 volts, and so you'll have 9 volts across the resistor. You'll have less than 11 there, and you'll be down in the safe zone right there. And moving on over, we have the 100 ohm resistor we're going to look at. So if you got the blue ones, this should be the color code that you see. There's a brown band on one end for the tolerance for 1%. It could be 1% higher or lower than the rated value. Same with the 1000 ohm. That's what it means. That's what the blue ones tend to be, blue resistors. But in any case, now we have brown for our first digit, 1. And then black 0, black 0. So 100 is 100. So we have this fourth band. That is a multiplier. Times 1. Black means times 1. Or you could think of 0 zeros. There's no more zeros. Just 100. 100 ohms right there. So putting a voltage across the resistor. Again, we have Ohm's law. The current, which they use I to indicate current. I think it meant intensity at one time. But in any case, I for current is voltage divided by resistance. So 1 volt divided by 100 ohms is 0.01 amps, which is the same as 10 milliamps right there. It is linear. As the voltage goes up, so does the current. So 2 volts, 20 milliamps, 3 volts, 30 milliamps, and so on. Now, again, wattage is not linear. So you double the wattage, or you double the voltage, I mean, you'll double the current, and you get 4 times the wattage. So that's how that works. Wattage goes up a whole lot quicker. So you can see here we can only put 3.5 volts across the resistor for 35 milliamps of current flowing through it, and we get 0.1225 watts right there, which is about halfway below, or a little less than halfway below the absolute maximum you want to put in there. So we can't deal with as high of voltages, but again, just like the 1000 ohm resistor I mentioned, you use like LEDs or something, other stuff in series with it to take away some of the voltage. You also put stuff in series with the 100 ohm resistor to take away voltage. So a good chance if you see, unless it's very low voltage, you may see the 100 ohm resistor. If you see it in circuits with a higher supply voltage, there's definitely other stuff taking voltage away from it. So it's ending up with probably less than 3.5 volts. Now we'll move on over. So I think I didn't want to focus on a particular resistor value too much. So we're going to another common value. A lot of times you'll see 2 followed by 2 in the numbers. A long time ago, resistors were expensive. They only came in certain values, and they didn't have the 1% tolerance where the value you saw is really close to what you're actually going to get. They could have been off wildly, and so you had some odd, I should say, number combination. But in any case, 2 followed by 2 was common, and it still is. So with a 5-volt circuit powering this load, that we're going to light an LED here. So red LED is what we're going to do. It's going to drop about 2 volts. It has a forward voltage of about 2 volts, which is dropped from the resistor. So this is the direction that it conducts more easily. If you put it in backwards with 5 volts, it's just not going to light up. You got to put it in the right way or no current will flow. So cathode, the short lead, heads to ground. Anode, the long lead, heads to the positive supply. I'm just doing kind of a quick review. I've done demonstrations of this circuit before. If this is all confusing, watch those. But in any case, now we have 5 volts across the whole load there. This is ground. Usually it's the negative side of the supply. It's considered 0 volts, and that is 5 volts higher. So there's a 5 volt difference between these two components. The LED, it doesn't conduct up to, it's actually less than 2 volts. But 2 volts generally builds up across it throughout the current range. Sometimes a little bit higher, sometimes a little bit lower, but it's relatively close to 2 volts. So in any case, once current's flowing through here, we should build up about 2 volts across the red LED, leaving 3 volts across the 220 ohm resistor right there. So I did the math there of the current we can expect. Again, Ohm's law, 3 volts divided by 220 ohms equals, and it's a long number there, but you can see it's about 0.013 amps, and then 6 there, which is the same as 13.6 milliamps of current, as I put there. Now this is a pretty simple mental math. We got the 1 and 3 there. Let's just go with 1 and 4 right there. And so to know the wattage, you take the current times the voltage. So it'll just be 3 times higher than what we got there. So it'd be 0.0. So first it'd be 3 right there, but 3 times 4, let's do that, would be 12. So instead of 3, it would be 4.2 right there for the wattage, but still way less than 0.125 watts, which is what we'll want to stay below. So the resistor is not going to get terribly hot in this circuit. And now we look at the example of the blue LED. So if you watch my videos, you're going to see me protecting a blue LED from 5 volts with 1,000 ohms quite a lot. We are ultimately getting about 2 milliamps of current through it. The blue LED drops more voltage than the red LED. The blue LED is going to stop current completely up to about 2.5 volts. You know, it might glow a little bit, tiny bit might leak through, but for the most part it is not conducting current almost at all. But at about 2.5 volts approximately, then it does start conducting pretty well and lights up fairly brightly. So we have a higher value resistor here, mostly because in my circuits, blue LED gets brighter than the red LED at the same current. So I find at about 2 milliamps of current, it gets about, the blue LED gets about as bright as the red LED at 13.6 milliamps of current. And now we'll zoom back a little bit. One thing with electronics, everything you learn with more complex circuit is just building up a whole bunch of the simpler stuff you learned before. So it's not like you're wasting your time learning this simple stuff and it's holding you back. You're actually learning the complex stuff, just one bit at a time, and then the complex stuff puts it together. So figured we would zoom back. As I said before, while we were up here, you'll see the 1000 ohm resistor in a lot of circuits that are 12 volts, even though you only want to put 11 volts across it. So now we have an actual example of that. A 1000 ohm resistor protecting a blue LED from 5 volts. Again, it gets really bright even at like 2 milliamps of current there. But the blue LED is going to be dropping about 3 volts. So out of that 5 volts, you ultimately end up with about 2 across the resistor with the blue LED. So you could power this circuit with 14 volts, and then dropping 3 volts out of that 14, you would have 11 across the resistor, and it'd be quite warm at that point. You won't want to touch it right away, but in any case, it should still be safe right there. Shouldn't overheat at any time, as long as it's exposed to air and stuff. You laid a blanket or something on it, it might overheat. But in any case, as long as it's exposed to air, then it shouldn't overheat. And now we'll add a little bit more to this. So generally circuits just aren't powered all the time, like an LED is just not constantly on with the battery always applied. This actually would probably indicate a 5-volt power supply. So this would be the positive side. That's the negative side. There's a 5-volt difference between them, so you consider 0 volts. The ground right there, 0. And then we have 5 volts higher, which would be the positive side of a 5-volt power supply. So now, switches, most switches just have 2 states where it's either open or closed. I have push button switches. They put them on a breadboard. They don't fit terribly well. You could adjust the pins or whatever to make them fit better and stuff. But in any case, I just push them in the breadboard till the breadboard gets used to it. You press it, it turns on. You release it, it turns off. So that is because I have normally open push button switches. There are normally closed push button switches, but I never bought one. They're a little hard to find. So if you have push button switches, I probably got normally open. So that will mean the LED is off when you have it in series right there. That is because you have a gap of air between conductors. And so air does not conduct very well. You need very high voltage and low voltage circuits. You don't have to worry about that. Current is the same through all series components. So if none of it can go through the switch, none of it can go through the resistor or the LED right there. The circuit is off. Now you can close the switch. So closed means there's no gap. So open is gap, closed is connected. So hopefully that makes sense. That's how it works. You'll hear a lot of just explanations where they just say open or closed. That's really all the word they'll use to explain what the circuit's doing. So it's good to get familiar with that. It'll be less confusing when you're listening to people explain stuff. So we got it closed. Now we have our connection from the 5 volts right there. And I rounded off the current because we looked at up in that corner there that it was actually about 13.6 milliamps of current that we calculated. Again, if you took an actual measurement, so to do so, you would open up the circuit between the negative supply ground right there and the LED. You would just leave air, and then you'd put the red probe with the multimeter after you set it to the right setting to measure current. You put the red probe to the cathode of the LED there, and then the black probe there, and current would flow through the meter, and it would tell you how much current is flowing through it. Again, current is the same through series components, so when it also goes through a meter, it's measuring the current going through it actually, but it's the same as the series component. So 13.6 as we said before, but I rounded up to about 14 milliamps here. So now moving on to the final drawing on this sheet, and so I'm going to end it here. We have 12 volts across a resistor protecting. In this case, it looks like it's probably a red LED. I drew it red over there, and because the red LED, or whatever LED this is dropping about 2 volts. So we can expect 10 milliamps of current. As we said before, 1,000 ohm resistors are easy. Usually they're abbreviated to 1K, means the same as 1,000 ohms. And so we'll have 10 volts across it, as we saw up over there before. That will keep the resistor from getting too hot, because we don't want to go above about 11 volts. 11 should be fine. 10 is close to that. So we know we're safe there, and we got, a fair amount of current here. So red LED might not get bright enough. So 20 milliamps is kind of high for a red LED, but if you really want to get the 20 milliamps there, that's its maximum current. We have a simple solution if we have 12 volts. So we don't want to go lower in resistance because the resistor would get too hot with 10 volts across it for the most part. So we can just put another resistor parallel with it. So both of these resistors will still have 10 volts across them. The red LED is going to drop 2 volts, pretty much no matter what's going on over here. 2 of the volts will be across the LED. It doesn't adjust really. Once you get above about 1.5 volts, current starts flowing, and it drifts up to about 2 volts. But in any case, it's a semi-rigid what the voltage will be built up across the LED. And it's like a release valve. Once the voltage is high enough, current's just passing through, so it can't build up anymore. Hopefully that makes sense. So in any case, we're dropping 2 volts from these two 1,000 ohm resistors. So that means that the current is going to go through that resistor and LED, not really caring what the current is doing over there. So same thing, the current's going to go through this resistor and LED, not caring what the current is doing over there. So both of these resistors are going to pass 10 milliamps of current, but they combine and then they both go through the LED. So we could measure like 10 milliamps over there and 10 milliamps over there, but if we measure the current over here, we will get 20 milliamps. They will add up right there. So hopefully that makes sense. And I did the math down there, but we did talk about this earlier. 10 volts divided by 1,000 ohms equals 0.01 amps. And so you can see 10 volts times 0.01 amps is 0.1 watts. So about the highest wattage we want to put through a 1/4 watt resistor.